Welcome to designing a small signal voltage divider bias amplifier. The objective is to provide the necessary steps for designing an NPN small signal bipolar transistor amplifier. The most popular design for small signal amplification is the voltage divider bias amplifier. The voltage divider bias amplifier circuit provides high stability, thereby preventing Q point shift due to variations in HFE. The voltage divider bias amplifier is shown in the following diagram. Please note that Vout is taken from the collector of the transistor. Therefore, it is 180 degrees out of phase with Vin. To keep it simple, Vout is an inverted output. This design procedure is based on general-purpose NPN transistors such as a 2N3904 or 2N2222, which have a minimum HFE of 100. Step number 1. We are to select a VCC. VCC is the power supply voltage that the amplifier will use. VCC typically is either plus 6 volts, plus 9 volts, or plus 12 volts, since these are common battery voltages. So let's go ahead and select 12 volts for our particular amplifier. Step 2. Select an appropriate voltage gain. Note that consideration must be given to the maximum amplitude of Vin and also the amount of swing that Vc can deviate from its Q point. Assume a maximum swing for Vc being about 80% of VCC. Based on the above constraints, the following equation can be used to select an appropriate voltage gain. The A sub V chosen should always be less than or possibly equal to 0.8 times VCC divided by the estimated maximum Vin, which is in a peak-to-peak value. Note that as gain increases, the stability of the amplifier is sacrificed. A maximum gain value of 10 is recommended. Let's select a Vin value, peak to peak, that will be no greater than 0.1 volts. Therefore, using this information in the equation above for gain, we have 0.8 times 12 volts divided by 0.1 volt. And the amount will be be 96. Now this is the maximum gain that this amplifier stage could have, but again, as the gain increases, we're going to have an amplifier that could be possibly unstable. So therefore, let's go ahead and follow the advice in that we should keep the gain to about 10. So this amplifier will have no problem in having an amplification of 10 because it could possibly go all the way up to 96, a gain of 96. But again, we do not want to go that high with a single stage of amplification because the circuit will be unstable. So let's go ahead and keep it to a gain of 10 or shoot for a gain of 10. So let's go ahead and write that down, that we're going to design our amplifier stage to have a gain of 10. Step number 3, select values for RC and RE that provide the gain selected in step 2 based on the following ratio equation where your A sub V is approximately equal to RC over RE. So here's what we have so far. We have the RC value. Well, we don't actually have a value as of yet, but we need to go and choose the A sub V as far as the ratio of RC to RE to be equal to 10. Now, one of the things that I do want to make a point of is that the RE value, which is the resistor at the emitter, that this value of resistance does affect the input impedance of the amplifier. So since it does affect the input impedance, it can't be very small. So one of the values which I would definitely shoot for is to have at least about 1K to make your RE value about 1k ohm. So let's go ahead and do exactly that. We'll make the R emitter 1 kilo ohms. So therefore, if we were to do this, if we let RE equal to 1k ohm, therefore in order to achieve a gain that's equal to 10, your RC value would have to be equal to 10k ohm. Therefore we have a gain that's going to be approximately 10. So from this equation here, we can make the RC value be 10 kilo ohms. Step number 4, assume a VCQ that is about 1/2 of VCC. Now granted, this is something that we can shoot for, but this can actually be lower than 1/2 of VCC as long as the signal at the output is not being clipped. So we have VCQ that's equal to 1/2 of VCC, which is equal to 1/2 of 12 volts, which gives us a VCQ that we're shooting for about 6 volts. What this means is that the voltage at the collector, okay, across to the emitter, and by that I mean the VCQ, that this voltage across here is going to be 6 volts. That means that the other 6 volts is going to be spread across the RC and RE values, because again the sum of the voltage drops from VCC, since VCC is equal to 12 volts, and if we know that the VCQ that we're shooting for is 6 volts, that means that 12 volts minus the VCQ, which is 6 volts, so 12 minus 6 is going to leave us with 6 volts. That needs to be spread across the RC and RE values. If we were to write this down as an equation, we could say that the VCC minus VRC minus VCEQ minus VRE is equal to 0. So that would be 12 volts. Now we have not solved for VRC. We have solved for VCEQ, which is 6 volts. And we have not solved for VRE is equal to 0. So 12 minus 6 leaves us with 6 volts minus the voltage drop across the collector resistor minus the voltage drop across the emitter resistance, and that's going to give us 0. So in other words, 6 volts is going to have to be spread across the resistor across the collector plus the voltage across the emitter resistance. Step number 5, calculate ICQ. ICQ is equal to 1/2 of VCC divided by RC plus RE. This is to figure out what the current is. Now the ICQ should be somewhere between 1 milliamp and 5. If not, we really need to choose different values for RC and RE while still maintaining the same gain ratio, and then repeat this whole process again. So let's go ahead and solve for ICQ. So our ICQ will be equal to 1/2 of VCC, since VCC is 12 volts, 1/2 of 12 volts is 6 volts, divided by RC plus RE. Well, that's going to be 10k ohm plus 1k ohm, which comes out to 6 volts divided by 11 kilo ohms. That gives us a current of 6 divided by 11k gives about 0.55. That's 0.55 milliamps. Please note that the ICQ, as was stated in the document, that it should be between 1 milliamp and about 5. But the issue that we have here at the voltage that we've chosen, that of 12 volts, the RE value was set to 1K. We could drop that value lower, but unfortunately it's going to affect the input impedance of the amplifier in that it's going to load whatever the VN signal is a bit more than what we would like for it to be. So one of the things that we should do then is to leave the RE value at 1K and just go ahead and keep the ICQ value as to what it is right here. So I'm not going to change it. I'm going to leave it as is, and we'll go with that. If the VCC had been a larger value, then we would have been in that range, but with 12 volts being supplied, then this amount for ICQ is okay. Again, the main reason for it is just because the input impedance of the amplifier stage that we have right here will actually become lower if we drop the RE value to be even less. So we're going to keep the emitter resistance at 1K. Step number 6, calculate the voltage across RC. So the voltage across RC is going to be equal to I times R. Well, the I that we're going to be using here in this equation is going to be that of ICQ, so that's 0.55 milliamps times the resistance of 10K, which gives us 5.5 volts. Step number 7, calculate VC. This is the voltage at the collector of the transistor. VC, therefore, is equal to VCC minus VRC, which is equal to 12 volts minus 5.5 volts, which is going to be equal to 6.5 volts. Therefore, the voltage at this point is 6.5 volts. Step number 8. Assuming an HFE of 150, calculate IB. Therefore, IB is equal to ICQ divided by 150, because ICQ is a current that's flowing down through here, through the collector resistor, and as far as the current that goes down through the emitter, of course, that's going to be IB plus IC. So the current through the emitter is equal to IC plus IB. But as far as to figure out the HFE, we know that HFE is equal to IC divided by IB. But we can algebraically rearrange that to solve for IB, which is, in this case, the ICQ is what we're going to be using in our equation, which is equal to 0.55 milliamps. And we're going to divide that by 150 to get the base current. The base current, as we can see here on the calculator, is going to be rather small. It's going to be equal to 3.67, and that's going to be microamps. Step number 9, we are to calculate VE, and to calculate VE, we need to figure out IE, where IE is equal to IB plus IC. So therefore, for IE, which is equal to IC plus IB, we're going to use the values of IB that are seen here, and we're going to use IC, which is the ICQ value right here. We're going to add those up and come up with the I sub E value. Even though this number is fairly small, definitely keep it in mind because we need to put in as many of the digits that we see here. All this is very important. So we have something that looks like 55.0037, and that's going to be milliamps. Excuse me. I needed to redo my equation because this value is incorrect. It is 553.67, and that's going to be microamps. Now, taking that value, as far as IE, we can figure out VE. VE is equal to IE times the emitter resistance. So knowing what IE is, since we just solved for it, and taking the emitter resistance, which is 1K, let's go ahead and figure out what the voltage drop is here. Which is 0.55. I guess I could round as well, so 0.554. So the voltage at this point in respect to ground is 0.554 volts. Now with that stated, we can figure out what VB is, what the voltage at the base is right there. And we're going to assume that there is a 0.7 volt drop across the diode that's internal to the transistor right there. Therefore, making that assumption, the voltage drop that would be incurred because of the diode here is 0.7 volts. Therefore, VB must be 0.7 volts greater than VE. So therefore, it would be at 1.254 volts right here. And the equation would be something like this. VB is equal to 0.7 volts plus VE. And that's how we arrive at VB. Step 11. Letting IR2 be 10 times the current of IB, calculate the value of R2. This ratio of current flow will allow a stiff base voltage to be present. When IR2 is at least 10 times greater than IB, the loading effects of the transistor are negligible and can be ignored. So again, we're going to take IB and we're going to figure out what the current is through resistor number 2. So that's going to be 10 times IB. Now I'm going to make room here. So what we're solving for now is for the current flowing through R2. So IR2 is equal to 10 times IB. Base current was figured out at 3.67 microamps, so therefore IR2 is 36.7 microamps. And since this current here is 36.7 microamps, we can figure out what R2 is, because Ohm's law, resistance is voltage over current. The voltage of VB in respect to ground is, well, why should I say, the voltage at the base of the transistor in respect to ground is VB. And VB was found to be 1.254 volts. And we're going to divide that by the current flowing through R2, which is the IR2, which is 36.7 microamps. So we have 1.254 volts divided by 36.7, and that's going to be microamps. And we're going to get a value of about 34.1 K. About there. Actually, we could probably round that to 34.2 K. K ohm. So that's the value for resistor number 2, for R2. Now for number 12, step 12. Letting IR1 be 11 times IB, calculate the value of R1. Since the current flowing through here, through IR1, is going to hit this node and then it's going to split, we're going to let the current through R1 be 11 times greater than IB, because if we have 10 IB flowing down through R2 and we have a single IB going into the base of transistor, then this must be 11 IB then, right? So therefore, what is the current flowing through R1? Well, that would be IR1. So the current flowing through resistor number 1 is going to be 11 IB, so 11 times IB. And that's going to be equal to IB is 3.67 microamps times 11. And that comes out to about 40.37 microamps. The next thing we have to figure out is what's the voltage drop across R1? What is the voltage drop across here? Well, since we know what the value of the voltage is at the base, and we know what VCC is 12 volts, which is up here, and we know what the base voltage is, which is 1.254. Therefore, the voltage drop across R1 will be 12 volts minus the 1.254 volts. And that's going to provide us with 10.746 volts. So this is 10.746 volts. With those two pieces of information, as far as R1 and VR1, we can solve for the resistor value of R1. So I can say that R1, that the resistance of R1 is equal to VR1 divided by IR1, which is equal to 10.746 volts divided by 40.37 microamps, which is going to be equal to so the value that we arrive at is at 266.2K. So it's 266.2 kilo ohms for R1. At this point, these are the values that we have for R1, for R2, for RC, and for RE. Now the only thing to try, of course, is to put it through either put it on a breadboard and try it out, place a scope to it, so on and so forth, both the input and the output, or we could possibly put into some sim software like LT Spice. But before we do that, let's take a look at the values of the capacitors as far as for V in and V out that should be used, or that could be used. Now, to make this complete, let's just hone in on step number 13 right quick. Granted, we found values, but you really need to find standardized values that could be used for your R1, R2, RC, and RE. Okay, step 14 was to select the input and output caps. For audio amplification, both of the capacitors should be about 1 microfarad to about 47. Now, we have a table here that shows the reactances of different cap values. So depending as to where you're at as far as on the frequency range and the value of the capacitor that you use will have a different amount of reactance. So for example, if you're looking at a capacitor of 1 microfarad, at 50 hertz it's going to have a reactance of about 3.2 k ohm. And if you're looking at it operating at 15 kilohertz, it reduces down to about 100 ohms. And you can see what the response would be for some of the other caps as well. So depending as to what type of frequency response you want will depend as to which value you would choose here. I would probably go with something about maybe a 10 or a 22 microfarad. That would probably be on the pick which I would use. Whatever you want to use is up to you. So let's go ahead and continue on. So for the capacitors here, make sure that they're of the electrolytic type. And granted, for sizes in the range which we're talking about, pretty much that's all there that is available. So let's go ahead and run it through some sim software as far as the values that we arrived at and see what kind of output we actually see and see if we actually arrive at a gain of 10. I've opened up LT Spice, so let's go ahead and start a new schematic. And what we want to do is grab all the components that we'll need. Let's grab an NPN transistor from here. Let's put that there. We need some resistances, of course. One here, another one there, another one here, another one there. And a capacitor. To 66.2. $34.2K. Alright, so I need to wire this up. Connect this here. We also have to place a ground down here. And we also have to select a VCC. Voltage right here. Place a voltage source right down here. And let's select that it's going to be a DC value of 12 volts. And we need to wire it up, of course. Alright, next thing, of course, we need to go ahead and select values for the capacitors. And let me go ahead and choose 10 microfarad. And the same over here. That should be sufficient. And we have to input a signal, of course. So we need to get another voltage source and place it out here. This is going to be the actual signal that we're going to send into the amplifier. So let's wire it up. The signal source is going to go here, and this one's going to go to ground as well. Connected right there, that'd be fine. Now for the source, we need to do a right click, go to advanced, and we're going to do a sine wave. And the DC offset of the sine will be 0. Amplitude is going to be 0.1 volts. Now that's 0.1 volts peak. Okay, so so that would give us basically a voltage of 0.2 volts peak to peak. So perhaps I should go ahead and do 0.05. All right, so it's 0.05, and that's just V peak. Then peak to peak would be 0.1 volts. And let's go with a frequency, say about 1,000 hertz. And let's go with that. All right. So now we can go ahead and run the simulation. I believe I've inputted all the values properly. Let's see. Now, the time to stop, I'm going to put about 0.05 5. Can't see where that ends up at. I'm not too sure. I might have to adjust that. But we need to start saving that immediately. And so let's go ahead and do that. I think that's enough right there. So what we want to do is we want to sample the input. And so that's what the input is right there. Now let's sample the output, which will be right over here. And you can see that the output is close to about a volt peak to peak. So we have an input that's about 0.1 volts peak to peak, and you can see that the signal is inverted. Now let me adjust some of the settings here, make it a little bit better. Let me go ahead and edit the simulation here. Stop time, it's way too high, so let me go ahead and reduce this. Let me make it 0.25. I think that might be a little bit better. And let me go ahead and run that again. Okay, this is a better view of it. So the green sine wave, that's what's being inputted into the amplifier. And the blue sine wave is what's being outputted. So we can see that the input is about, as we stated, okay, peak to peak, it's about 0.1 volts. 0.1 volts, peak to peak, that's being sent in there. And the output, as we can see here, is going to be approximately about 1 volt peak to peak. So it indeed does have a gain. We know that the gain is going to be equal to your A sub V is equal to your V out over your V in. So therefore, if you have an input of about 0.1 volt, which is again is 0.1 volt peak to peak, and your V out is about 1 volt peak to peak, therefore you have a gain of 10. And that's what we're shooting for. That's exactly what we were shooting for. So this shows you that the amplifier does function. Now, the thing that would be interesting is just to see what the actual output signal is based on frequency. We can edit that right quick. And since we had, and what I want to do, let me go ahead and stop this right quick. I need to edit this. Let's change the frequency to 10,000 just for the sake of it. And let me run this again. And let's see. Okay. I still have to edit a little bit more, seems like it. Okay, I adjusted it. And so now we're able to view the output here. And again, we're getting close to about 1 volt peak to peak at the output. Okay, so it hasn't changed all that much. So this amplifier is working as it should, works very properly. And again, I would definitely stick to the value of R2, or your RE I should say, your RE value, which is the resistor at the emitter, of about 1K. And granted, again, because it doesn't affect the input impedance of the amplifier. So if you're going to attach one stage after another, we really need to have a high input impedance to each of the stages. So by having at least 1K as your RE value, you're ensured to be able or to avoid having to load whatever the signal is as being inputted. And that is all I have. Thank you.